it starts really clean, but it becomes a hairball. And what ends up happening is you cannot automate change.
Parantap. Been looking forward to this for at least a month. How you doing?
Good, good. It's so good to see you, Nick. I was also excited to be part of this.
That's great. Thanks so much for taking the time, being with everyone, as well. You're like one of my favorite people, believe it or not. It's like, because whenever we talk, I always learn something really new and in ways that I never, where I might be able to look at a problem and, and you look at it and you have a different view of it. And I always learn from that. So I'm always like, I'm always excited to talk with you, and
Good to
you've
hear.
had like this really great background too. Like you've, really worked on some big problems, as well. So, I thought the way that we would probably start, is, to give you some time to kind of talk about your career journey, and how you progressed, how you got started, like even like, we've been trying to, within the community, bring people in that, maybe are, have been thinking about, joining our industry, but maybe they're a little intimidated, or maybe they're not quite sure, so, I would even like, okay, what even brought you into, IT and computer networking?
Sure. Yeah. Uh, I was always intrigued about networking, even when I was completing my degree in electronics and telecommunication engineering. And I didn't have any course on networking at that time when I was finishing the degree. But I was so intrigued about it because we used to do all this programming and everything in a regular computer with its own memory. And you see the results in the screen. But I thought that how could you talk to another computer that is on the other side of the room or another part of the world? And it intrigued me. I didn't know how these things happen. And whenever you have something that creates mystery, you have to go for it and you cannot stop before you understand more about it. But as luck had it for me, after I finished my college through campus, I got into a company who were bringing internet to India. And I was one of the four engineers who were chosen on that particular project. And it was way back earlier in the 90s. And that experience was so fascinating for me because all the protocols that we kind of use today, like BGP, ISIS, OSPF, and whatnot, those things were in draft format at that time, and we had to put
Mm.
together networks and configure them using those protocol. And like my nature goes, I cannot use something if I don't know how to use it. Like, protocols are just tools,
Yeah,
and you have to know how to use them effectively. So knowing them is one thing, but knowing to use them is something else, right? So I used to
totally.
read
Yeah.
the IETF drafts on my way to office, and it was very interesting time. And I was fascinated how things were done in way it can scale because internet is a global scale with so many different 10,000 plus networks, and each network having thousands of devices. It's humongous scale. It wasn't like that at that time, but it actually intrigued me. So it was a great experience to start to putting together the first internet in India. And then fast forward few years, I found myself in the backbone engineering team of UUNet, which is one of the first commercial ISPs in the US. And
Yeah.
I started working. So one of my mentors at that time asked me, saying that, "Hey, you want to understand network? Work on the multicast network, the AS704 at that time."
Oh my
And it
God.
was extremely, you know, extremely.
A hard problem.
Uh,
Yeah,
it,
just do the multicast thing.
yeah, and everybody like they knew it exists, but nobody wants to go, like that kind of a stuff.
Yeah.
But and I was the new guy, and I was asked to do it, and like my nature, I started digging into how it works, and I had a great mentor, Jeremy Hall, who was an expert in the multicast network, and it was complicated. We used to work with Cisco all the time because there are OS issues and implementation issues. And some of the people who used to
Hmm.
solve it are friends of me now. At that time, they were
Yeah.
God, like they knew everything. And so, so multicast gave me a really good understanding of how protocol works and how scaling works and all those things and how state creation works and all those things. And then I had a chance to go into the unicast backbone, which is the AS701. And later on, I
Yeah.
became the manager of that team, doing the network engineering team for AS701. And, I think what I learned during those days, I'm still caching it. It's still
Yeah.
carrying me through. There were such brilliant mind in the unit, original unit team, and the way they understood protocol scaling and resource scaling and chattiness and why should you use this protocol and that protocol. I still go back. It connects so many dots for me. And then I met some of the people who wrote those ITF draft that I used to read when I just got out of college. And
Yeah.
the way they looked at the world, their worldview, so fascinating.
Mm.
It's amazing. I think that kind of set me off for the next part of my journey as a network professional. Later, I went to Microsoft to run the network architecture team for their online services. And
Yeah.
Microsoft at that time was it was 2005 at that time, and they were just using traditional enterprise IT layer 2 switching domain, spanning tree, and those kind of
Yeah.
network topology, and they were just duplicating it inside the data center to run their service. But those kind of network topology and protocol usage has issues. They're not meant for scale. They're meant for
For sure.
complexity. They're meant for campus network and very small enterprise data center. So one of my, and this was pre-Azure, pre all this jazzy thing that
2005.
Microsoft has, right?
Yeah.
Bing even. I think Bing was in its
Mm.
infancy at that time. So
Mm.
then the goal that my boss at that time, Najah Muhammad, he's an awesome guy, and he later went to run the Facebook network. So he said that,
Mm.
hey, figure out like what should be our future. And I remember the day when he came to my office on the whiteboard. He just wrote few different topics on the whiteboard, and he said, hey, I'm going to come back to talk about it in few months. And he just let me think about how to scale this and how to really bring sanity into that madness. So first I
Mm.
standardized there were like 10 different ways to deploy it, and I standardized it. And then
Yeah.
essentially Azure was coming in. And the other important part was there is another team inside Microsoft called Microsoft Research. And they're like
Hmm.
really sharp, really brilliant
Yeah.
people who come from the
Yeah.
academia. And they are so hungry to solve real world problems. And I came from
Mm.
the real world because I used to be in the production network and engineering the production issues. So we used to meet every other week or every week even. And I used to spend hours in Building 99 of Microsoft Research. And then I used to talk to
Mm.
them about, hey, these are the problems, spanning tree, it's so weak and fragile and there's so meltdown. And, layer 2 protocol like Ethernet frame doesn't even have TTL, that is time to leave counters. So once you have a
Mm.
loop, it creates a storm, it melts things down. So that's the time
Yeah.
when on the other side, other online services were getting built. So clause kind of topology showed up. And
Yeah.
then the question was, people who were doing clause, they were writing their own protocol. And I came uh,
So just so everyone
from
kind of
the back.
knows, Parantap,
Huh?
so
What's that?
CLOS, like CLOS, non-blocking,
Uh,
fully connected,
yeah,
backbone, from I forget the
right.
the scientist's name, CLOS, but it's named after him. Yeah, but anyway, so just want to
Clo,
make
I
sure
think
everyone kind
they
of
pronounce it
following along.
Clo.
Okay, yeah.
That's exactly it, and they name it Clo, and
Oh,
there are few
yeah.
other topologies like that. But the my since I came from the ISP backbone background, so
Yep.
the wide scale network or wide area network protocols like BGP and RSVP, MPLS, and those things were my second nature because that's where I grew up. So I said that why don't we just use BGP and eBGP for that matter, not even IBGP, and then why can't we
Yeah.
run this class? Why do we have to write our own protocol, right? And that's when it started, and we had some really good engineers from our vendor side also, from Arista side. So we all kind of innovated together, and we came up with the first Azure Fabric, which was essentially topologically, physical topology wise, its class, which is a cross mesh of different, like you were saying, uh, network devices, which runs BGP as a protocol, which is really different from how you build a switching network using spanning tree, which has to be a little more root and tree based protocol. So fascinating time there in Microsoft. We also worked on
For
software load
sure.
balancing as opposed to hardware load balancing, because hardware load balancers were really expensive and you cannot build a cloud service doing the processing on hardware load balancer,
Mm,
which are essentially x86 CPUs inside. So what are they doing that the rest of the CPU farm cannot, right? So we did that kind of work. Okay, let me pause for a second and I'll go for the next part of my
yeah.
journey if you have any question.
Okay. Yeah. Well, I think this is a really good preview as to like, because we're going to dive
Mhm.
into like, the future in a moment. So,
Okay,
so whenever you're ready.
right. Yeah, sure, sure. Then I came to Bay Area
So
from Pacific
Microsoft high
Northwest.
performance computing. Yeah. So
Right.
Microsoft high
And
performance
so
computing, class, BGP in the data center. Yeah.
right, right. So that was there till 2012. And, so Azure started around 2008. And then I was there for the
Yeah.
first 4 years of the network build for Azure. Then I came to Bay Area to join a startup who were doing SDN on creation of the VPC. So essentially, it's the similar work that I was doing in Microsoft, but they wanted to use BGP as the control plane protocol as opposed to something
Ah,
custom or just open flow and those kind of approaches. So I found it pretty intriguing. I thought it's a problem that has to be solved. And so I joined the startup. It got acquired by Juniper. I was in Juniper for another 4 years. And then I was doing similar work on that SDN product. And then in 2016, I joined eBay because, in certain ways, in a product company, you have some kind of excitement, but in company where you are operating a network, that's a different level of excitement, right? So
yeah.
essentially, in one case you are building the plane, the other one you're flying the plane, or whichever way, or building
Right.
the car and
Yeah.
driving around the car and that kind of stuff. So in 2016 I joined eBay to run their network operation team. And then I went to, in 2018, I went to Visa for a year to run their network operation. And I fell sick and I had to go through a surgery. So I was looking for
Uh,
another job back in South Bay. So I came back and joined eBay, which is in South Bay. So,
uh,
so now I take care of eBay's data center, network infrastructure, as well as their server hardware. So all the server hardware innovation. eBay
yeah.
is an on-prem company. We build our own hardware. We run our own
Yeah.
network. So that's my job right
Okay. Awesome. Well, okay. So now you are so perfectly, experienced to kind of have this next level of discussion. All right. So so first of all, maybe before we leave, so eBay, what can you say? Obviously nothing proprietary, but
now.
around the size and the scale, of that. And
Hmm.
also, how are you thinking about scale these days? Because actually the way that I'm starting to think about scale is kind of different. It's I'm starting to really think of it differently, but I can share that with you. But what's your
Hmm.
so eBay kind of network size scale, like how are you thinking about that?
Sure, sure. So eBay is predominantly on-premises company. We don't send all our workload to the public cloud to run it. So that puts us in a unique position where we know where we build, how we scale, and a lot of these things are under our direct control. So it has multiple regions, and each region has multiple data centers inside it. But it's a global company. So these regions are
Yeah.
predominantly in domestic US, but what we have is something called POP, which is the points of presence. You can think of it as micro data
Hmm.
centers all over the globe. And these are the POPs. In the POPs itself, we connect to the internet, and we have thousands of connection with internet across the globe. So in the network infrastructure, what comes in is, of course, you have the network infrastructure that is needed to connect the server racks inside a data center, then the data
Yeah.
centers with each other inside a region, And then you have the backbone, which connects all the POPs and all these core data centers with each other. And then you have some of the security services where you have the defense and the perimeter defense and all those things that come in. So that kind of constitutes the overall network infrastructure. Now, with respect to eBay scale, eBay has been around for like 30 years. It's as old as the internet. So
Yeah.
it collects more than few petabytes of data every day, depending on the transaction that happens. It handles billions of transactions every day. I think it carries 2.3 billion listing, and the scale is kind of humongous.
Yeah.
But at the same time, the people who work in the infrastructure are pretty smart people, so they understand how to handle disaster recovery and how to scale it out. It's almost like a mini cloud infrastructure here, like hyperscalers
Mm,
have cloud infrastructure. It's a
yeah.
miniaturized form of that.
Yeah, that's huge scale, like a few petabytes a day. That's big. That's really
Yeah,
big.
that's good.
So, and I'm sure it's growing. It's like some of the numbers that
Mhm,
we've seen is like kind of like 50% growth in data. Over like a couple of year, 3 year time frame. So that kind of like brings me to like maybe the way I'm starting to think about infrastructure now. It's like
mhm,
very data oriented, so
mhm,
it's not so much of like our job, and you were kind of going through that in the very kind of the front end of the podcast, was okay. We're connecting things together. We're utilizing tools like BGP to kind of like provide logical kind of connectivity on top of that, and to control how traffic is steered, around that, so that we have really strong control points within that infrastructure. But the main point is to connect things, computers, other kinds of things, into an infrastructure. And correct me, or if you have a different view, would love to hear it. But I'm starting to think now it's really Pablo actually introduced the concept where the network is more of an exchange, right? And really what we have is data coming into this exchange, and the network is really providing an exchange from applications that need data, users that are providing data, and so it's a different kind of way to think about how the network operates. So for example, as we start to like maybe see AI come into this, I'm sure you're seeing this already. We see very different data patterns. We see very different data gravity centers, within your infrastructure. Latency requirements change. They're not kind of static east west north south on the edge, what have you, but the whole
yeah,
latency requirement starts to shift and change. The relationship between applications and that infrastructure, where the applications is requesting a service, and that could be a connectivity service with a security wrap, around it. Then the infrastructure, starts to allocate, those services. It's a little bit more futuristic view of it, but I think that's I'm starting to kind of think of like our industry and our job from that point of view, and especially as we get, AI more deeper into the protocol sets and agents like into it, to start managing the lifecycle operations and the day-to-day operations of that. So I don't know. That's what I've been, kind of thinking of lately. What's your view?
you covered a lot, and there are a lot of things there, and a lot of really, really interesting topic and what you covered. The way and Pablo was 100% correct, and he actually hit the nail on the head. So if you look at the overall infrastructure, it is basically pool of resources. So you have GPU compute is a pool of resource, CPU compute is a pool of resource, and then storage, be it distributed, be it centralized, it's basically pool of resources. And then network is another pool of resource which connects all this pool of resources. And
Hmm.
if you look at the success of a good, well operating infrastructure, it's essentially how well are you utilizing this pool of resources, because some of them are very expensive, like GPU is very expensive, and if a very expensive pool of resources is left stranded because a relatively cheaper pool of resource was not built the right way and is acting as a choking point for an expensive pool of resource, it's not good design, right? It's basically, you have
Mm.
to build these things in a way where all access to all pools of resources for different kind of computing needs, or even storage access need, or whatever way a particular workload works, it has to be put together in a proper way, right? So my philosophy, and this is something that I picked it up from Microsoft, and when I started thinking about it, and this is something uh, became clearer and clearer every day, was you need to make a network resources like air and water. So network should not be custom built or custom or in a way tailored to meet a particular application need and stuff, because what ends up happening is you deploy something, and that infrastructure has to be around for 5 to 6 years, if not 7 years. And what
Mm.
you build it up for, invariably, if you build it up in a very custom way, in a tailored way, you are going to get congested and this and that. And it's very hard to sustain an infrastructure over a longer period of time, because things change, application
Mm.
pattern change, behaviors change, and that kind of stuff. So what I've been trying to do is, essentially the idea was, how do you move the complexity to the edge, so that
Mm.
when you have simpler building blocks in the middle of the network, then uh, it gets a lot easier, because if you bring in complexity into the middle, then it has to
Yeah.
be expensive, right? And you
Mm.
cannot scale. But if you make it simpler, self-similar, uh, then you can even go towards commoditization. Like, you cannot have complexity and commoditization in the same sentence, because you have to, in order to make it commodity, it has to be simple, self-similar, and the failure domains have to be contained, and a lot of things has to line up, right?
Mm.
So to come down to comment on your thoughts, what we have done in eBay, for that matter, is we have a really fat, flat network, which is,
Mm-hmm.
think of it as, between all the servers, you have 8-lane highways connecting each server, right?
Mm-hmm.
And then you have 16-lane highway corridor and stuff. And these things are all built using open source. Like Sonic is the open source, like the roots
Yep.
were there when I was back in Microsoft, but they actually contributed it to open source in 2017. So
Yeah.
I used Sonic, and then I used white boxes. White. There are a lot of white boxes. Actually, the OEMs themselves use white box, and then they put their own operating system on the top of it. So we directly go to the white box. We use open source operating system, and then the way we build the network is, uh, the class topology kind of comes in, but there are
Mm-hmm.
varieties of class, and based on how you use the class, like what is your topology, the oversubscription you impose on the top of rack or on the fabric can be determined, right? But the goal is,
Yep.
how can you build a wide enough network at a cheap enough price point using the right
Yep.
kind of technology speed? Because you have to understand industry really well. For
Mm.
example, you have to know that around this time, 400 gigs is going to be commoditized. Now,
Yep.
when we say 400 gigs is commoditized, that means the optical transceivers are cheap, the silicon itself is cheap, then the cables that you use to connect the switches are cheap, and there are a lot of technology cycles that you have to watch out for, and then you build a fabric which is the biggest possible fabric you can build at that point of
Yep.
time, or in the vicinity of that point of time, and that creates the network becoming air and water.
Yeah.
And that's
Mm.
what we have done. So, and that's what,
Mm.
it's not about, hey, the industry should go open source versus closed source or whatever it is. If you have a network where the core is simple, and in an open source Sonic, the protocol is run by a container which runs FRR, free range routing, and only thing you can run inside it is BGP, eBGP, to
Yeah.
be more precise, right? And then you don't have to have other IGPs like OSPF or this and that. And if you're not carrying as
Mm.
much complexity, it's a very simple protocol. Then you design the policies, the routing policies, and all those route filtering policies and stuff, and the community tagging. You can really build air and water grade network fabric which connects all the resources with each other. True
Yeah.
for data center,
Mm.
not as much true for campus network or more complicated
Yeah.
enterprise, but that has been my philosophy, and we have
Yeah.
been walking that path.
Actually, thanks
Yeah,
so much for sharing that. So, like, um, kind of low cost complexity out of the core of the network. You move the complexity as much as you can out to the edge, which I'm assuming is kind of into the servers, right? When you're thinking
right,
about the edge, right? So, kind of
right,
where you have
right,
compute, you have storage, there. So, kind of put those services out there. You leveraged open solutions like Sonic. It's a great idea. Obviously white boxes, wide range of options, around white boxes as well. Um, that's a great model, and also you've done it at scale. So it's like anyone who's out
right.
there is thinking, oh, does this scale? Yeah, it does. If eBay,
It does.
is doing it, then
Yeah,
anyone can do it. And also, a lot of the hyperscalers, have a kind of a similar, I think, architecture, as well.
right.
Clearly, Azure does. So is there? So now, so I get all that. That's great. Parentap.
Mhm,
The operating model. I think
mhm.
the biggest challenge that many felt with kind of an open solution was, okay, how do I manage that? What are the tools that I use? Do I have a
Mhm.
throat to choke? If something goes wrong, so
Yeah,
what's
yeah,
the operating model kind of look like? And like,
yeah.
what is your knock?
That's
Do you have a knock?
yeah, absolutely. I do have a knock, and I think if you split this complexity into piecemeal, things get a lot more easier. And so typically, what people think is, hey, if you want to go open source, you have to hire 10 engineers who knows how to actually contribute code to the upstream and make sure that you have the code. But it doesn't have to get that complex. So what I
Yeah.
did was I pretty much there are some startups in the industry and there are some OEMs who are delving into Sonic. And I initially went into the OEM model. I said, hey, you know what? Just give me a Sonic a Sonic binary which works on your code,
Mm,
and let's get our hands wet with the Sonic, and I'll have the team going with that. And then I worked with a startup, and then essentially I got some of the Sonic support through the startup. I didn't have to hire those 10 people in my team to do it. Of course, in my
mm,
team, I have a pretty solid network engineering team, and they're experts in automation and they know Sonic inside out. And but I don't go and support Sonic. I leverage a startup to do it. Right now, when you talk about network complexity or the operational complexity, what ends up happening is in a regular network, in a regular enterprise network, change management is a big deal because
yeah,
change
huge. Yeah,
management is and change management is something that brings in complexity all the time. Because if you look
yeah,
at the roots of change management, it is always atomic. And networks are built in a holistic way with some protocols and some standards of configs and stuff. And now, in an atomic way, somebody would come in and say that, hey, can you add this VLAN here? Can you? And then there was an outage and you added some default route somewhere and you forgot to remove those default route, or you have you have a new network config that you turned on only to satisfy a particular customer. And in a more complex network, you have OSPF getting redistributed into BGP and vice versa. It becomes a hairball a little later,
mhm,
right? It starts really clean, but it becomes a hairball.
yeah,
And what ends up happening is you cannot automate change anymore going forward,
yeah,
because if you have to automate change, you have to understand where you are putting in the change. Like, you can use Ansible, and there are so many different things to put in a change, like few configs for the change. But if the place where you're applying the change, you're not confident that the configuration is what you thought it is, then you have to first discover, like, how does it look? And is the
yeah,
change going to sit well, right? And that kind of complicates the whole thing. And it's so hard to automate changes. Simple changes like shutting one port or unshutting one port, adding a static route, simple, but
yeah,
complicated changes are really hard. So what we did
yeah.
was, and this is something that I had in my mind, but we had some brilliant network operation engineers here as well as network engineering engineers here. So we said that, you know what, we are not going to have changes which are atomic. Changes come in, there are 5 type of changes or 8 type of changes which are very cookie cutter. And when the changes happen, like you want to cost out a device or you want to cost out a link, and those are the kind of
Mm,
changes. So why don't you have the base layer config done, and the cookie cutter config changes should be automated in a bulk. And when you remove
Yeah.
them, like when you're costing it in, they are also removed in a bulk. So what ended up
Right.
happening is you have a very consistent infrastructure which was born with a particular set of changes.
Yeah.
Then you have database which says that, hey, this device is in maintenance mode, so, or this is in installation mode. So forget all the signals and stuff this device is generating, which cleans up our network operation management plane a lot more, way more. And then you have all the change management done, or the config upgrade and all those things done in a very automated way. So the idea was, how can you wash your hands off from the atomic changes, which kind
Right.
of spoils the whole thing, right?
Mm.
And on the other side, for the network management piece, which where the operational, so there is a code management piece, like, hey, if there is a bug in the code, who
Mm.
is
Yeah.
supporting you, right? And so that's where we have the third party as well as some in-house resources. And then the other thing is, how do you operate the manage the network, right? Because there is SNMP pool and all this traffic, all the syslog
Right.
has to come somewhere, SNMP has to come somewhere. And that's where I also innovated with another company, a startup, and they were working on AI based network operation almost 7 years back. Now AI is pretty hot,
Mm.
but they were kind of out there almost 7 years back. And they invested a
Yeah.
lot in supervised learning, unsupervised learning, and they went a long way. So my, if you know how network management works, it's pretty simple.
Mm.
What happens is you have this whole network screaming at you, saying that, hey,
Yeah.
my BGP is down, hey, my port is down, and all these things. But what happens is, if a link is down, most probably two two network devices are going to scream, hey, my link is down. And then both of them are going to say, my BGP is down. And, for a single event, it ends up becoming 10 alerts that shows up,
Yeah.
right?
Right.
So now
Yeah.
you have to throw in a system in front of them saying that, hey, no, 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 not 10 alert. Tell me what exactly happened so that I can work on it. But even if
Yeah.
you look at those one thing, the signal to noise ratio, we talk about it.
Mhm.
Even if you talk about the signal, there are pages and pages of signal. Some of them are important, some of them are simple, like, hey, this device is getting installed, so all the ports are down, so don't worry about it. And it becomes pages and pages of alert. And then you have the
Yeah.
knock people who picks up some alert saying that, oh, this is huge, so I have to create a ticket for people to work on it to basically restore it. And
Yeah.
the typical network operation problem is people get lost in the alert. And what ends
Yeah.
up happening is the application sees the issue because something has gone bad in the network. And then they say that, hey, what is going on in your network? Tell me. And then they now start digging into the tickets and the
Yeah.
alerts, and they
Mhm.
get lost, and it takes 30 minutes to figure out what
Mm.
happened. And
Mm.
then they costed out a device by changing the configuration by hand, atomic change,
Mm.
and it's
Yeah.
really bad, right? So what we did was we said that, okay, we have to invest heavily on how to improve the signal to noise ratio. And I
Yeah.
hated alert console because I had 13 pages of alert console. I said, hey,
Mm.
team, why don't you make the signal to noise ratio so strong that you can create a ticket out of it? You know,
Mm.
if
Yeah.
if you're not having a ticket out of it, why it is even creating noise in your
Mm.
console, right? And the team worked
Yeah.
on it. And basically now what we have is, from the operation, if there is an issue, it correlates and cross correlates and using AI a lot, and not generative AI, the traditional AI. And now we see completely tickets showing up in our dashboard, and people work on it to take care of it, right? So,
Yeah.
this whole sonic
That's
thing and network operation thing all goes hand in hand. How you build the
mm.
topology, how you build the architecture, a lot of things are interconnected.
Yeah. Well, one that's huge. So I would think. Do you? I'm not sure if you're at liberty to tell. But like the number of changes that you make maybe in a year. It's like one of the on one of our board companies, one of the banks, they go through about a million a year, like a million
Hmm.
changes a year. It's like huge,
Yeah.
and also like and on the number of alerts too. But I wish I had those numbers off the top of my head. On what the numbers are for like some of the large companies, but they're astronomically high. So kind of like um, filtering those out and getting to like root cause as quick as you can so you can actually cut a ticket. That's got to be a huge operational savings, and also just reliability and uptime savings as well.
Yeah, yeah.
So, so on the number of like changes, like if you can share,
Mhm.
like how many changes you guys like
You
normally
know,
experience like in a year.
yeah, I don't have, honestly, I don't have anything on the top of my
Okay.
mind, but let me
Yeah.
give you the journey on this front. So,
Okay.
there are two kinds of changes. One kind of change are manual changes where people going in
Yeah.
and making atomic changes, and you have a change ticket and they're following the SOP there and that kind of stuff. And then there are other kind of changes which are automated changes. You have to roll the password in the device and those kind of stuff.
Oh.
And when you see millions of changes, it is actually both. So that's
Yeah.
why there cannot be million of manual changes. So if you look at the number of manual changes, it would be in order of few thousands at the most. But rest
Oh.
of it is all automated changes, right? So at one time, when before we were in this whole identify the total what change are you trying to bring, costing out a device or costing out a link, and then apply the change holistically and then pull it out. Before that, when it was atomic, we used to have a metric saying that how much downtime are we taking because of change. And
Hmm.
and there were
Oh.
numbers
Yeah.
like, hey, there were 50 minutes of downtime or 3 minutes of downtime or whatever it was, because invariably when people are cutting and pasting a change and you don't, and there are 200 lines in the config of the switch, and you scan the config, but humanly like you will miss things because
Yeah.
it's a human eyeball scanning the config and digesting it, and you then paste a change and suddenly everything went dark, and now you are on the console and you are rolling back the change and said that, hey, it was the change didn't go successfully. Yeah, you took 5 minutes
Yeah.
of outage or something, right? So, and
Yeah.
then that actually impacted the uptime. So now we just, I don't have that metric. It's gone.
Yeah.
For the last
Oh,
4 or 5
perfect.
years, it's gone. Because that metric doesn't even make sense. Because if you have a change issue, fix your automation. Like there is no,
Yeah.
you don't have to ask human to be more diligent. Like this
Hmm.
whole human centric way of, oh, somebody is slacking, somebody is lazy, they're not smart enough. Large scale network doesn't get built that way, right? It has to be built in systemic
Yeah.
way.
Yeah. That's a great way to think about it. If you're getting inundated by the changes and their manual, like you're doing something really wrong. It's like
Exactly,
it's
exactly.
time to automate that. You know.
Yeah,
So
but it's
let's.
harder, way harder said than done. Because if you have a brownfield environment where all your
Yeah.
processes and everything is connected through atomic changes, a single person cannot come in and change the whole thing. It will, they have to be very
Yeah.
senior and they have to have 3 4 years of time to clean it all up. Yeah.
Yeah. So then, Parentap, let's kind of like think a little bit about how AI impacts our industry. Whether that's
Hmm.
from kind of a design point of view. Like, do you think like the designs that we have built already, like for example, the design that you have put
Hmm.
in place, do you feel like that's going to be able to support, either new AI applications or any other applications? So like it's
Hmm.
both, kind of, the network to support AI, and then also
Hmm.
you were mentioning before, especially around alert mitigation. Having
Hmm.
kind of a company that was working on some AI that would actually be able to filter that out and reduce,
Hmm.
the noise, so you get a bigger signal. Are there other
Hmm.
areas like where do you see kind of AI impacting both
Hmm.
your infrastructure and the industry at large?
Yeah, AI has brought in an angle which is really fascinating. And, so what happens is you build this infrastructure which is meant for cloud and cloud computing workload. Like it's all the sessions
Mhm.
coming from the internet and all this requests, and you are kind of doing it in some latency which is in order of milliseconds, right? Now, when AI came in, AI had two different workloads. Like it's to to break it in a little broad way. One is training, and the other one
Yeah.
is inferencing. So basically,
Right.
training is you're training the model with a lot of data, but once the model has been trained, you can use this model to serve the question, the request, and you can actually use a different infrastructure to do the inferencing part of it. And the nature of these two workloads are slightly different, because for the inferencing part, it is requests coming from outside, saying that, be it a chat GPT query or whatever it is, it's coming from outside and then you are responding to it. It doesn't have to be the training infrastructure that is responding to the inferencing call, because you take the model, typically you quantize it and you basically make it smaller, and then you deploy in a different infrastructure, and you can serve it from there. And inferencing is load balancing and the traditional cloud compute way of delivering the service. Now, the network requirement for both are slightly different, though in
Yeah.
inferencing there is an angle where things are trying to merge. So for training, especially if it is a large model pre-training, foundational model pre-training, they have to get trained where all the GPUs are constantly communicating with each other. And for every stage, there is front
Hmm.
propagation, back propagation, and there is a lot of coordination needed. What ends up happening is, if network is not there to provide that coordination, essentially the entire thing slows down, because all the
Right.
GPUs that are actually doing the training job, they have to be in the same page, right? So that's where all the InfiniBand versus the new Ethernet, UEC, the Ultra Ethernet Consortium, those work is
Yep.
happening. And that's the backend part of a large training cluster, right? Now, and a lot of interesting work is happening there. And InfiniBand itself actually does a pretty good job. But Ethernet is a lot more ubiquitous and it has the economies of scale, so it has its own
Yeah.
benefit. So there is that part. So from our point of view, we are watching them both out pretty closely. And
Hmm.
if we have to build a dedicated backend, we will build a dedicated backend. But currently we have InfiniBand and it works. Now for the
Hmm.
inferencing piece, if you have the models are getting smaller, and they can be served out of a single GPU or a board of GPU which has 8 GPUs inside, and you don't have to go across multiple GPU node. But on the inferencing, there is a small nuance. So inferencing can be broken down into two phases. One phase is the prompt phase, and the second phase is the token phase. So the prompt phase
Hmm.
is like, if you ask ChatGPT a question, it takes time before it
Yep.
puts the first token to you as a response, right?
Yep.
So that phase is very, very compute intensive. It
Mm.
needs a lot of T-flop. But once it has generated the first token, the next phase is the token phase, which is more memory intensive. So now, if you think
Yep.
in terms of stranding of resources, like go back to the original discussion where these are basically
Mm.
resources that are deployed and we should not strand resource. So if you are
Yep.
running a lot of inferencing on a single GPU node, which has run out of memory, but it has a lot of T-flop remaining, or vice versa, it has run out of
Yep.
T-flop but has a lot of memory remaining, then the question is, hey, can't they all work together and move the
Yep.
KV cache from one node to another node and do a better performance utilization? That part is there, right? That work has to be there.
Mm.
And if you need a different network for that, yes, we are going to do it. But we are analyzing all those things, right?
Yeah.
So
Yeah.
coming back to your other question, if I heard it correct, so on the network management piece, how can Gen
Yeah.
AI or AI can help? You know, it's very interesting again, because one thing is,
Mm.
right now, if you look at a regular network operator, they have so many different systems they have to interact with in order to
Right.
troubleshoot something, or in order to have a diagnostic tool spawned to do certain things. And every operator has to learn this thing, and they have to spend 3 months in the network to understand all the tools and stuff. But if you look at the Gen AI opportunity, you can integrate it with Slack. You can say that, hey, tell me
Mm.
which
Yep.
network got upgraded or switch got upgraded yesterday. Like, it can Slack can integrate with our change management system. So all the way how you understand to interact with the rest of the system can be all made conversational through a Gen AI interface. And that's one of the
Yep.
opportunities. So people can talk to the entirety of the system in a conversational way and get a lot more. And it can even be action oriented. It need not be only LLM, you
Yeah.
can say that, hey, can you run this diagnostic tool to see if this particular switch is doing all right, if all the hardware is fine, if the local log is clean and everything, right? So you can do it. And then the other opportunity is in the agentic AI, you can think about if you have a Sonic running switch, which is open source, you can run an
Yeah.
agent on the top of it, right? And you can
Yeah.
ask that agent, hey, can you tell me, are you sick or are you doing all right? If the
Yeah.
agent doesn't respond, it is sick, right? Because the agent is not
That's a
responding.
surefire. That's a
That is
sure sign.
your
Yeah.
sign it is sick, right?
Yeah.
Or the
Yeah.
agent can run detailed diagnostic on the switch itself, and then it can report back, I'm fine. You don't worry about me, and you move on.
Yeah.
Like if you look at the old world, the only visibility you have in the box is basically through SNMP and syslog,
Yes. That's.
and so
Yeah.
constipated. It's mind-boggling, right? How can you
Yeah.
troubleshoot a situation and then people have to log in? So a lot of opportunity. I'm so excited about AI.
Yeah, that's a really great the Sonic and the agent, like an agent per device. So you have like now this network of agents that can be,
Right,
kind of monitoring the entire infrastructure, and so
right,
getting to root cause a lot quicker, and then also interacting with like the tools that you were just mentioning, before. So you could have maybe kind of a level one, engineer, that has all of a sudden these powerful tools that that now they're it's like skilled as like a level two, or
right,
I'm not sure about level three, but it
right,
upskills them and it gives them a much greater visibility. And I think maybe when we start to like sum all of that up, it really just talks towards a much more reliable and also just greater uptime resiliency of that infrastructure, being able to kind of find
right.
problems when they arise a lot quicker and then address them and keep the system up and running.
Exactly,
So I think
exactly,
that
exactly.
right.
Yeah, yeah,
So what
exactly.
about like how applications interact maybe with those agents. So maybe like one concept has been is that maybe there's kind of an agent of agents, right? So you have almost a
Mhm.
controller of agents, and those kind of controllers can interact with applications. So an application
Right,
kind of requests a particular service, and then that controller now can actually look all across the infrastructure, and maybe that application consults policy, and the policy has got to have this kind of latency. It's a highly secure application, so it has to have end-to-end encryption associated with it. It has to
yeah,
stay within the United States, and the data can't go outside of
mhm.
the U.S. So it has
Yeah,
all of
yeah,
those policies with it. What you're kind of thinking on that kind of transaction happening, where the
yeah.
applications can act. We have machine to machine communicating with each other based upon policies that we set forth, that dictate how they operate.
Yeah, I think, AI is almost like electricity, where you don't know what it's going to do going forward. Like people, when they invented it,
Yeah.
electricity is doing so much more. So things will evolve, right? It has so many things, ways to evolve.
Yeah.
The fundamental technical gotcha is this. So what happens is when you are having an AI sitting on or an agent sitting on a node, it has the understanding of what the node is doing and whatnot, and it is healthy and all those things, right? But what it doesn't know is the sessions that are going through the node, because it's very hard. It has millions of TCP sessions going through the node, and exactly having the chipset knows, and maybe there are ways to get it out through S-flow and stuff, and there are some work that has happened, like all the records that are all the five tuple of the TCP session or UDP session that is going through the node. So
Yep.
the agent might not have direct access to it. Maybe it will have it going forward. But now, if you look at how applications interact with the network, is essentially through these sessions. So, for example, I'm a server sitting on the side, and I typically get 20 millisecond of latency to reach out to my other endpoint of another server that I typically communicate with. And now suddenly today it's 50 millisecond. Or typically I
Hmm.
get 700 megabits per second throughput for a particular session, but suddenly today it's 35 megabits per second of throughput, right? So now the question is, why is it happening, right? Everything
Right.
has to be solved from the point of view of what problem are you trying to solve? Now, how
Yeah.
would this agent would go to troubleshoot it, right? So first of all, what happens is you have to identify, you can give a major swipe and say that, hey, all agent, tell me, are you dropping a packet? And what you're going to find is there will be 20 agents saying that, oh, in my link, there is a 2% loss in this link and that link and this and that. But you don't know why this application is like, who is going to go and cross correlate with those 20 devices and this thing? Hard problem, right?
Yeah.
So what
Yeah.
happens is you have to understand, and then between two servers, there are 500 different equal cost paths to go from point A to point B. So,
Mm.
like if you even have a health hello going between two server, it's going to take
Yeah.
one of those 500 paths, and your session is taking another 500. So it's going over a
Right.
completely different set of switches. It's in the best
Yeah.
case, it's going to lie to you that everything is fine, right? So, so, so the
Liar.
idea is, so the idea which is very interesting is, you know uh, we have to find out, like we have to track through AI what is the normal range of TCP throughput between two endpoints, and what is an anomaly, right, before even the
Yeah.
application sees it. So capture the data. Now if you have an
Oh,
anomalous data, then find out what is the endpoint and what is the five tuple. Then you have to find out which path the five tuple is going. First of all, if you can find out the path it is going, that's easier, but it's easier said than done. You have to be, there are few tricks to do it. You can put the port number, the destination source port, emulate the whole packet and send it, and find out where the path is going, and you can investigate on that path. The other one is, overall, for every agent, they can actually ping every other hop. They need not ping the immediate hop, because if you ping the immediate hop from an agent, the packet goes from the CPU to the
yeah.
outgoing interface of the hop. But if there is a fib corruption or some issues, not even link error, a fib corruption issue on a particular switch, the packet is coming from one port and going to the other port. So these are
Yeah.
two different use cases. So you have to simulate something where the agents are generating enough traffic, which is exercising the forwarding plane on the switch port itself to identify, is some switch getting confused, or if some switch has a fib corruption. And then you can cross correlate the whole thing. Essentially, the part where I'm talking about the packet actually going through the switch, that's data
Yeah.
plane, right? Now the
Yeah.
control plane is BGP and all those things. Management plane is SNMP and all those things. These three planes, like, okay, fine, BGP, the control plane will reset if the data plane cannot pass three hellos or something. But
Right.
typically, most of our diagnostic is based on our management plane, which doesn't
Yeah.
capture data plane as much. It only captures error rate and in octet, out octet, those kind of thing. But if there is a
Yeah.
gray failure or something which is complicated, they cannot find it, right? And that creates a blind spot. So AI
Yeah.
can actually really help. The agent of agent
Yeah.
concept can really help, but you have to know the real issues you're solving, you know?
Yeah, that's a really good point. So it's like, well, if it's supposed to be so superhuman, it should be able to figure out all the different use cases, and be able
I
to kind of
know. Yeah.
sort all that out, for us,
Right.
But I know,
Yeah.
Parentap. I think we're kind of getting close to to the end.
Yeah. Okay.
Any I know it's like, I think your analogy was like so right. This is almost like the early days of Thomas Edison and electricity. We just don't know
Right.
like all the different
Right.
applications that are going to be coming from AI. But do you have a strong view or a strong thought, on how you think our industry is going to like change with the onset of these new tools that come into the marketplace,
Like
AI
with respect
tools?
to networking, you mean with respect to
Yeah.
networking?
Well, you can
Yeah.
expand beyond networking if you like. It's like you see
Mhm.
lots more than just the network infrastructure. So
Right, right.
yeah,
Y- I look at the agentic part of AI, and, a lot of ideas spawn in my mind, and I wonder where the business sense will make a case for it versus not. But it is like the amount of data that we are collecting and the way people typically has been interacting with the data in a very process, rule set oriented way, versus where AI can come in and process the data and find some patterns inside it and understand what can go wrong. I think it opens up so much possibility, so much possibility.
Yeah.
You know, so there is a buzzword thing that people kind of go after a certain angle where it's cool to call AI, say everything is AI, and try to solve the problem. But deep
Yeah.
underneath, there is solid value. There's solid value.
Yeah.
So people can get distracted saying that, oh, it was just a hype cycle and it's over. But for AI, it's not true. It's
Yeah.
basically there is deep-seated value, and people who really know the problem space, they are going to use to solve the problem space the right possible way, right?
Yeah.
So from the network side itself, traditionally we have a centralized network monitoring and management system. And now, if you think in the AI way, how you can distribute the whole thing. Like if you look at what we have been
Yeah.
doing, we have been bringing all the hay inside the haystack. And then we are saying that where is the needle? And we are putting so much effort to find out the needle, where you can actually identify the needle on each device itself. You don't have to bring it along with the hay in a centralized haystack. And those kind of capability AI can provide you. It can scan the local
Yeah.
log. We never look at local logs of every device. We all look at the
Yeah.
syslog, which it sends out. But all the problems are logged in the local log. You can use
Yeah.
AI to scan the local log, find some anomaly, and then flag it. Like, hey, this doesn't look all right. Can you take a look, right? And people can go and take a look, right? So, the opportunities are limitless. I think it is going to challenge some of the paradigm itself. And, networking, beyond networking,
Yep.
the way networking is going to work with application stack, that's going to change,
Yeah.
because at one time, people had to manage the data using rule sets and stuff, which is impractical. But now, if you have somebody else to manage the data, you can join the bridge a lot more easily, and brilliant things will come out.
Yeah. It's fascinating. I love the haystack analogy. That is so good. You're right. We've been trying to suck data out of all these different devices, centralize them, and then we have this massive amount of data now to kind of sift through. Yeah, that's absolutely
Yeah.
right. That's what a great
All right.
analogy.
All
Awesome.
right.
Parentap, this
All
has
right.
been phenomenal. Just so enjoyed chatting with you. I now actually going back to my first comment. You always give me a different way to kind of look at things, and you did that here. So thanks so much. It was really just great.
Thank you so much, Nick. It was great talking to you. Thank you.
Awesome, great.
Bye.
Thanks, Parentap. Thank you everyone for plugging in as well.